It's the time to have our sixth speaker in this session. So we'll have Jakub Banaśkiewicz from Jagiellonian University in Krakow, and he will be speaking about periodic orbit for the Brusselator system with diffusion. Please.
Okay, thank you for a nice introduction. Okay, I will talk about outgoing research, and this is joint work with Piotr Kalita, my supervisor, and Piotr Gliczyński. Okay, so let's investigate Brusselator system. Okay, it's a system of coupled partial equation, and we assume Dirichlet boundary condition on one-dimensional spatial domain. This is this interval 0p. This system can describe some chemical reaction. Okay, and this reaction can give rise to some periodic behavior, and there are some nonlinearity in this reaction, and this can come from this reaction that 2u plus v creates 3u. So this reaction here corresponds to this nonlinearity in the system here. Okay, and for this system with there are results about existence of global attractor, but to my best knowledge there is no result about dynamic of this system and the structure of the global attractor. Okay, so let's go into numerics. Okay, so we will consider Galerkin projection on the space of eigenfunctions of second spatial derivative, and for one mode for each variable u and v, and with no diffusion coefficients, we have following ODE, system of ODE, and for b equal 1 plus 3 over 4 times a square, there for these parameters there should exist periodic orbit that arise from some unstable point. Okay, so numerically we have found periodic orbit for Galerkin projections with various parameters. Here is a list of some of them. For example, a equal 1, b equal 2, d1 equal 0, 1, d2 equal 0.001. Okay, this parameters describes diffusions, and we can see that diffusion on for the u is much larger than diffusion on the second parameters. And if we take them equal, for example, like we put 0, 1 here, there will be stable point instead of this periodic solution numeric. Okay, so let's show you animation of this periodic orbit. Can you see screen? Can you see video?
No, we cannot see the video.
Okay, so I don't know if I am. Maybe I'll try to share again. Okay. So, okay, can you see now?
Yes.
Okay, great. So let's observe that this, okay, it's starting from some initial value and goes to periodic behavior. And let's observe that this solution is symmetric with respect to line reflection to the line y equal p over 2. Okay, I will have to switch to presentation now. Okay, let's go share. Okay, so I am back to the presentation. And how can we prove this claim rigorously? We can use some C0 algorithm for rigorous integration Brusselator system to show that some Poincare map have a fixed point. Because this fixed point, because this Poincare maps is, because this fixed point, I mean, this periodic orbit is attracting, so it should be enough to use Schroeder-Fixed theorem. Okay, we can express our problem, Brusselator model, in terms of infinite ladder of ODE if we express U and V in Fourier basis, and we get these equations. Okay, so this corresponds to linear parts in these terms, and these terms and corresponds to this nonlinear parts, and we have on the first mode of U we have forcing that that comes from one of the reaction, and this nonlinearity is a form of this plot that is taking that is the sum over integers that sums to the mode that we are considering, and with some sign that comes from multiplication of indexes. Okay, and let's see following remark that corresponds to this animation, that the space of for which odd coefficients are equal 0 is invariant for this problem. This is due to this forcing that is only on the first mode. Okay, and this corresponds to the space of function which is symmetric to the line y equal p half. Okay, and I will discuss now how we can integrate Brusselator system rigorously. We divide modes into two blocks: one finite dimensional and second infinite tail. Okay, and we assume that for this finite part we have sets, some sets that are represented in computer as a vector of intervals, and sets that represent the infinite tail are represented by sets like, for example, in this form. So we have two numbers that represent these sets. These are sets that coefficient on the kth position are less than c over k to the s. But we can use some other sets for that. But we have to represent them by some finite numbers, finite numbers of numbers. Okay, and the goal of C0 solver is find sets that will contain that we also divide into this finite and infinite dimensional blocks, and this finite dimensional block will be such that the projection of the first mode, so the first mode will be in this block. In this block we get after the time delta t0, and these modes and these further modes will be also in this sets that we describe by some numbers in the time delta t0. Okay, we can observe that this system of for the first mode we can write equation in following way. We divided this equation into two terms. Each of them. One of these consists linear terms and terms that comes from nonlinearity, which depends only on the first n modes, and this contains other terms for the projection. Okay, and if we assume that we can estimate this this R function which contain other terms for t from 0 to this delta t for every solution with initial data in our set, we can rewrite our problem into form of differential inclusion, which is we have this function f1 and f2, which were before, but here instead of this reminder we put bounds on this term, and we expect that this bounds will go to 0 as we increase our finite dimensional block. Okay, and to do that we need to estimate this term. How can we do this? We need to find enclosure for our solutions. Okay, so we need to find, again, we divide this enclosure into two blocks, and these blocks for finite dimensional part comes from some estimation on finding positively invariant set in L2 or some other spaces, and so we need some estimates on that we have that our initial value are in some positive invariant set, or we can use local estimation or in L2 or some other spaces from Duhamel principle. Okay, and sets for tail are set in such a way that these equations holds, and because this comes from the system that if this equation holds, then this will for every u in this enclosure, then this will be for every u in this set, then this will be enclosure, and we need to check this inequality for k greater than n. So n is the number of modes that we are considering. Okay, and we can also compute this sets that will in similar way that will contain that describe this infinite tail. Okay, so if we have enclosure, we can rigorously integrate differential inclusion this and obtain set that will contain our solution in the time delta t. And solver for differential inclusion is implemented in CRPD library, and by integrating using this iterating this procedure will produce bounds that on Poincare map, and we hope that we can get that image of Poincare maps will be contained in initial set. Okay, so what is the research plan? Okay, we have found some numerical values for which Brusselator has periodic orbit. And then we try to check that there exists this proof existence of this periodic orbit for Galerkin projection, and add the small perturbation to the vector field, and this gives rise to the differential inclusion, and check if this differential inclusion, and check if we still able to prove existence of this orbit for this differential inclusion. Okay, and this is partially done, and other work that we have left is derive estimation needed for computation of enclosure, and the last goal is to rigorously integrate Brusselator model and prove existence of periodic orbit. Okay, thank you for your attention.
Thank you, Jakub.
Some bibliography.
Yeah, bibliography. All right. Are there any questions or comments?
I have a question. So thank you for the talk. So for the Brusselator model, you can also have, I mean, depending on the diffusion parameter, you can have Turing instabilities, and so also non-trivial steady states. Do you know if the orbit you found is in a regime where you also have this non-trivial steady states, or do you expect that it's the only interesting object, say, for these parameters?
I'm not sure this, because in case of Dirichlet boundary condition, it's harder to predict.
It's Dirichlet.
It's harder to predict some Neumann instabilities, but maybe I am not sure. Okay. And this is one-dimensional problem, so there is no some effective patterns like in higher dimensional problems.
Okay. I see. Thank you.
Other questions or comments? So I have one. So let's say right now you are aiming to prove a stable orbit using Schauder fixed point. So let's say that your research plan works and everything is done. Afterward, how would you be able to adapt this to unstable orbits? Would you have to change completely the approach, or you would?
I think Daniel Wilczak gave a talk about covering relation in infinite dimension, and I think it could be adapted to this. This could be used because this is some. This allows to this covering relation allows to prove some fixed point, but with that there are when there exists some non-contraction directions.
Okay, so the approach would have to be kind of changed a bit, right?
Yeah, a little bit change because Schauder theorem would not work here.
Yeah, I understand. All right, thank you.
I guess you need a C1 integrator to do at least to do the covering relations.
No, I think covering relation are at C0, but I'm not sure. Some con conditions are C1, and but I'm not sure. I'm not an expert, so sorry.
No. I think you're right. Yeah.
Okay. Other questions or comments? Well, if not, let's thank Jakub again. Thank you very much.